Let's get started. Let's go on with the next slide. So, welcome. We're so excited to have everyone here today for our introductory exploration of ROVs. Just to, review some logistics before we start, we appreciate all questions and everything. So, please drop those in the Q&A and then we'll get to those after. So now thinking about why are we here today? So as we know, you are all students that are learning more about what you might want to do in the future. And since the our team is interested in STEM, we wanted to offer an opportunity for all of you guys to learn more about STEM in a pathway that you could possibly take in STEM. So let's introduce the team. My name is Faz, and I am a first year engineering student at UW.
Hi, my name is Rishi. I'm a second year computer science major at UW.
Hello, my name is Evan. I am a first year computer science major at UW.
I'm Sylvia. I'm a first year engineering student at UW.
Yeah, and unfortunately, Brian wasn't able to join us today, so we adapted this presentation to be a little bit shorter to accommodate that. All right, so let's keep going. So first, let's start off with what an ROV is. We've been throwing this acronym around a lot, and some of you guys might not be familiar with what it actually means. So it stands for Remotely Operated Vehicle, and as the name suggests, ROVs are vehicles that can be accessed and controlled remotely, which can be really helpful in a lot of different applications that we'll talk about. So the first application that we're going to look at is space exploration. So I'm sure we've all heard the word rover before, and I'm not sure about you guys, but I always thought that rover was just a word, but turns out it's actually an acronym, and it stands for Remotely Operated Video Enhanced Receiver. And as you can notice, it sounds pretty similar to ROV, and maybe that kind of means something about them being similar. So let's think about the different functions of a rover, and for me, the top things that come to mind are how they use cameras to scout and observe a planet's surface. They use lots of different sensors to collect data on things like temperature, soil composition, and lots of other things. They use wheels and whatnot to move across different terrains, and they have all sorts of attachments and manipulators that they can use to collect samples. Now, another application is drones, and there's honestly a lot of different ways that we could use drones. For example, we could use drones in a search and rescue application. So imagine you went hiking and for whatever reason you got lost, you got stranded, and first responders know that you're missing, but they can't figure out how they can get to you. So right now, current methods might include sending out more first responders to try and find you, or maybe if you're lucky and the area has it, K9 units that are can pick up your scent and chase you. But what what's the point? We're putting more lives at risk that could also get lost. Maybe conditions are dangerous. We don't want to put more lives at risk. So, for example, we could implement drones that would be able to scout the area and search for you, and then they can lead first responders to you or can lead you to first responders. Another application in the same scenario would be delivering first aid kits or whatever sorts of medical supplies a person might need in case of emergency. And speaking of deliveries, like taking medical supplies, we could also think about maybe revolutionizing Amazon, right? Amazon involves taking packages from all over the world and sending it to different places, like right to the front of your doorstep. So we could start reducing on carbon emissions through, trucks and drivers and everything, all those resources that get wasted by implementing drone systems that are able to carry everything straight directly to you. And we actually have a video then of something that is already starting to be implemented that's similar to this drone idea. We can't hear the sound. Still nothing.
Getting it last time just through my mic like this.
Phone deliver them with the push of a button
Yeah,
on my
Does that sound half
yeah,
decent?
that works.
Okay.
phone. A few months ago, Mark Rover made a video talking about Zipline, a drone delivery company that makes life-saving medical deliveries in places like Rwanda. This video alluded to the fact that drone deliveries could become a normal thing for everyday products. Spinning motors! Three, two, one. To my surprise, I learned that drone deliveries don't just exist for life-saving medical supplies in Rwanda, but you can get almost anything delivered by drone right now. Okay, it's on its way. Okay, delivery's about to come. This is the area. It's supposed to hit right here, high probability area. If there's some wind, it'll go a little bit further out right here, but delivery should be here soon. Drop from the sky. Ooh, look at that. Chocolate chip cookies.
All right. Now, another application which I personally find the most interesting and is my favorite is marine science. So, similar to the application that we talked about for space exploration, there are lots of ways that we can use ROVs to explore underwater and understand the things that are happening on our planet. So, in similar theme, let's think about the different components that might be on an ROV that's used underwater. So there might be cameras that can be used to scout and observe the ocean's floor, or even marine activity, looking at how different fish are interacting with their ecosystem. They can also have sensors that collect data on, again, temperature, maybe the acidity of the water, the pH, and all sorts of different things. Instead of wheels, it can use propellers to reach areas that we've never documented before, so reaching lower depths and whatnot. And also, again, using different attachments, manipulators that can be used to collect samples. And I'll pass it on to Evan now, who will talk some more about specific applications.
All right, so we are part of MATE, and MATE has various challenges that sort of simulate things that might be done in the real world. So here are some examples of some of the challenges we've done. So, for example, one might be removing biofouling from a floating solar array. And biofouling is encrusting marine growth and like algal marine growth that are maybe reducing structural integrity and reducing efficiency and inhibiting the performance of a solar array. And so a task might be to remove that biofouling from the solar array. And so, for example, in MATE, this was represented as these pipe cleaners and these little PVC pieces. And you would need to construct a robot that is able to extract these. Next slide, please. Another example, again with solar arrays, is having to connect them to an energy grid. So this task would involve having to take off a cap and plug in a plug into these solar arrays, allowing the energy to be used from them. So we can see from both these that these are very like practical economic benefits that these are providing. Next slide. But there are also some environmental benefits. So, for example, this task would involve having to heal coral with probiotics, having to place this apparatus around the coral that provides probiotics and helps nurture the coral back to life. And so a robot would need to place this apparatus around the coral and then activate it. And those are some examples of some tasks that you might need to do and some things that ROVs can accomplish.
All right, so now we'll go into a little bit about last year's ROV that we used. And so here I have a diagram which has a picture of it. But I think that instead we will go into the CAD that we have of the ROV here. So I'll just pull up that diagram that we had to the side so we can reference it. And then I'll be able to show you guys some of the parts of it on this physical model that we have here on my screen. So I'll start off with where we keep all of the electronics. Obviously, this is going in salt water, and so that would be pretty bad for almost any kind of electronics. So we have all of the motor controllers, the computer on board, and all of that inside of an acrylic pressure hold, and that is this component that I have selected here in orange. This has only one opening out here at the back where we have this aluminum plate, and we have some of the motor wires coming out of this plate here through these special connectors that allow us to maintain that waterproof connection. And if you look on the outside of the ROV, you'll see these thrusters, these black circular bits here. Those are what allow us to push against the water and move the ROV. We can do things like change the orientation of the ROV, and we can translate it in any direction using these thrusters. There are a few safety considerations that we have, not just for the competition, but they're also pretty important just as we work on them. You'll notice we have some guards here and not modeled in here, but these sharp corners and stuff like that will have covers over. And so it's just in general some of the things that we think about. Besides that, we also have sensors on the ROV, which allow us to do things like Faiz was mentioning, able to see. That's a pretty important thing for an ROV. So here we have, if you can see here in the front, one camera there. I'm not sure if it's modeled. It is. There's another camera we have here at the bottom, which allows us to see it from the bottom as well. So how do we actually do things with this RV? Well, we have these modular manipulator slots in the front here, and that's here we have this gripper mechanism where my cursor is. This one's actually using both of the manipulator slots, where here we have one motor and we have another motor down here. And what we're able to do is we're able to switch out this block and the block at the bottom as well to be able to put on a different thing. Maybe we need a gripper, or maybe we need a different shape or something that rotates. So we're able to do a lot of different things with this same platform with that modular design. I think I'll go into some of the electrical things that we have. This is our electrical SID. It's a diagram kind of explaining all of the interactions between different electrical systems. We have here surface, which denotes our surface station. This consists of a laptop which connects to our ROV. And so we have a tether, which isn't pictured here, but it's a really long cable which connects from the ground to the ROV in the water. And through that, we're able to feed 48-volt power and Ethernet to connect our laptop, which we're controlling. It has a screen and it has basically a gaming controller that we use to control the ROV. And then that communicates with what's called a Raspberry Pi on the ROV. That's pictured here in green, and it's basically just a really small computer that our ROV is able to have. And that Raspberry Pi connects to all of these motors through what's called an electronic speed control, or ESC. And so you'll see those lined up here. This whole line is a whole bunch of ESCs which are responsible for basically powering the motors. And so there are a lot of other details here, but I think that if anyone has specific questions, I'm happy to go over those at the end. But yeah, as a good high level overview, these are kind of the systems that we have here. And so we have different teams working on kind of all of these different aspects of the ROV each year. And so, yeah, those are the highlights. We have the power, Raspberry Pi, motors, cameras, and some other mechanical aspects as well. And moving on, we have a video of our previous ROV.
Yeah, so as we watch this video, there's no commentary on this video, so I'll give some commentary about what's going on. As we saw in the video, the ROV is performing different tasks in the pool, and these are replicating during the mate competition. These are replicating the different tasks we might do in real life, like the ones that Evan was talking about before. And then now we have a video about the software that we have created and implemented that could be used on an ROV underwater to analyze different things. So you can start the thing, I'll give commentary. So here we have an algorithm that's able to identify different things that are in the water. Um, and you can see right now our RV is scanning what's going on. And here it's located an organism that it's going to look more at and it's able to track and collect data on it as it's in the water. So now looking at just some kind of final takeaways, we know that there are lots of different unique applications of ROVs in STEM, ranging from space exploration, rescue efforts, drone systems, and our own specialty in marine science. So if there's anything that we hope you take away from this webinar, it's that there's so many opportunities waiting for you out there, and you just need to take the first step to learn more and explore. And we know that there are several of you that might be applying to colleges right now, building your own college list or deciding where you want to go, and possibly even University of Washington. If you do end up joining us here, we really uh, hope that you come check us out. There's always so many different projects for us to work on, no matter what your major is. And of course, even just looking at our own team, we have people of all sorts of majors. And with the greater UW ROV team, we have people working in business, in English, in marine science, marine biology, just regular biology, physics, chemistry, all the engineering disciplines, computer science, and there's so many more. So there's always lots of different ways you can get involved, even if you're not in a specific STEM major. So with that, that concludes our webinar. We want to say thank you to everyone for joining us and also for people who are watching on the recording as well. If there's any questions, please feel free to drop them in the Q&A or unmute or anything like that, and we'd be happy to answer them.